much everyone for coming. Maybe I should come over here. Thank you very much everyone for coming. We are live streaming this, and maybe a few people watching on the internet as well as the people in the room. I'm Dave Woods, professor here at Southampton. So thank you for coming along to the MSG Design and Experiments seminars this afternoon. So we've got 3 talks, and without further ado, we'll crack on with the first talk, which is by Irene, Garcia, Camacha, Gutierrez. And she's from the University of Castilla-La Mancha in Spain, and she's going to be talking about robust design for mixture experiments and application to solve a real problem for diesel fuel cell companies. Irene?
Thank you. So, good evening. I'm going to present the work, Robust Design for Mixture Experiment. This work has been developed jointly with the professor Raúl Martín. Both came from the University of Castilla-La Mancha, which is in the center of Spain, and the university has 4 campuses, and we are in Toledo campus. So, first of all, I would like to briefly introduce the guidelines of my presentation. I will start giving the reason for arising this research, and defining the problem of mixture design. Then I will describe briefly the theory of robust design, and the original contribution of this work are contained into the section 3. To sum up, I will give you some concluding remarks and the open lines of research and the most important references used in this work. Well, the theory and methods developed in this work arise from a real problem laid out by the machines and motor area of the University of Castilla-La Mancha. They are developing a new kind of engines, HCI engines, for the acronym Homogeneous Charge Compression Ignition, which is a promising combustion concept based on the combination of traditional spark ignition and compression ignition. In other words, HCI engines are hybrid of traditional gasoline engines and diesel engines. Since the mixture of air and fuel is produced outside of the combustion chamber, as in a gasoline engine, while the autoignition is produced by compression, as in a diesel engine. What are they so interested in studying this kind of engines? There are mainly 2 advantages, and the first one is that they keep a good fuel economy. In particular, their performance with half load is higher than in a gasoline engine, and on the other hand, they provide very low nitrogen oxides and particulate matter emissions, so they agree with the most stringent regulation about pollutant emissions. However, there is a key point which have stopped its launch in the automobilistic industry, and it is that it's necessary to improve the autoignition process. In HCCI engines, it is a kinetically controlled process, differently from traditional engines in which it is a physical phenomenon. So autoignition is extremely sensitive to the charge composition. So our goal will be to determine the optimal surrogate composition simulating diesel autoignition. However, when we start to set this problem, we find 2 drawbacks. The first one is the experimenters have little information about model adequacy at design stage when there are not observations yet. In particular, they used polynomial models, but they didn't take into account the model misspecification at design stage. So a strong criticism of optimal experimental design theory is that design are strongly model dependent. So optimal experimental design theory is not enough when there is a lack of knowledge about model adequacy. So the idea was to use the theory of robust design. However, we found that there was a few works in the literature devoted to robust design for the specific class of mixture experiment. So our second goal is to develop theory and methods for constructing optimal robust design in mixture settings. Well, the classical definition of a mixture experiment is one in which the variables controlled by the experimenter are proportional. This feature implies that the design region is a constrained region. It is a Q-1 dimensional simplex, defined by the constraints that the proportion must be non-negative quantities and they must add up 1. So our goal will be to find a mixture design, which is an allocation rule of the experimental units over the simplex. In this work, we have considered two kinds of design, exact designs and continuous designs. The mixture design have received a classical design approach. Although many aspects differs from one experiment from the others, standard design has been used by practitioners. The most popular ones are simplex lattice and simplex centroid design. This kind of standard design has been suggested for a specific class of model which we'll detail next. So we have to choose a model linking the relationship between the responsive and proportion, and it also depends on a vector of unknown parameter plus an error term verifying the condition of the Gauss-Markov conditions. Well, the ordinary polynomials are not appropriated for this kind of behaviors, since the estimation of the parameter is not unique due to the collinearity between proportions. So instead, the CF canonical polynomials are the most widely used for being sufficiently flexible for a large number of practical situations. They are reparameterization of the ordinary polynomials. There are several versions available in the literature for explaining this behavior. In this work, we are going to use the CF polynomials in its intercept form, since take the advantage of saving one variable. The last proportion is implicitly determined throughout the relationship 1 minus the rest of proportions. Well, the theoretical framework which has been used in this work about robust design is the following. We consider that the form of the model is approximate linear in the parameters, and a more realistic framework is to consider a class of possible responses. In that sense, the expectation of the response can be written as the considered model plus a contamination function. This contamination function belongs to a 13th class of functions, although there are several neighborhood structures available in the literature. We have selected for this job Haber's class of functions for being enough broad and for covering a wide range of possible responses. The Haber class of function is defined by the regressors and the contamination functions to be orthogonal to guarantee the definition of the parameter to be unique. And on the other hand, it is a full L2 type of neighborhood, which depends of their neighborhood radius. Well, when bias occurs, a measure of design quality is the mean square error rather than variance. It depends on a term depending on the information matrix plus a bias term. Depending on the proposal of our research, we can consider the mean square error of the model parameters or the predicted response. And they have the following formula, assuming homoscedastic error, common variance, and mild assumption over M and A matrices. Well, so how to take into account both streams of error due to variance error and bias error? In this work, we have adopted a minimax strategy. It consists on determining the design minimizing the maximum of a real evaluated function of the mean square error. This function is known as a loss function. Thanks to a result given by Beans in 1992, we have that the maximization problem over the Haber class of function can be equivalently said as the following problem. It is to seek the maximum eigenvalue of certain class of matrices. Well, the most popular loss functions in robust design are defined from the classical alphabetic optimality criteria. So we have considered in this work the D loss and the I loss in the sense of the classical D optimality criteria and I optimality criteria. Well, note that we have defined over that definition a new parameter, nu, which depends of the neighborhood radius and the variance of the errors, and this parameter takes values from 0 to 1 and must be selected by the experimenter regarding the relative importance of the errors due to bias rather than variance. Well, now we consider in the case of binary blends that the response is approximately second order effect polynomial in its intercept form. And now we face a problem. It is that although the existing strategies of construction for robot design are general, they can only be applied when we have an analytical expression of the eigenvalues of the previous matrices. So, and it is not direct. So, in fact, these robust design works only have been calculated in a toy examples where a lot of assumptions have to be considered, definitively far from realistic framework as a mixture experiment. So we have to develop some theoretical result in order to simplify the problem and to get an analytical expression of the eigenvalues and in order to apply these existing strategies. Well, first, we are going to transform by an affine transformation the design region. It can be considered without loss of generality, since the D loss, in this case we are considering only the D loss and continuous design. It can be assumed without loss of generality, since this criterion is invariant by that kind of transformation. And let us define the subset of symmetrical function belonging to Haber class of functions. And on the other hand, let us define the symmetrical subset of design. Well, from that, we are able to establish a necessary condition to prove when a symmetric D-optimal design is the global D-optimum. Although this theoretical result, we need a practical rule to check this condition, and it is given by the theorem 2. The sufficient condition for a symmetrical design is D-optimal robust is that the second coordinate belonging to the maximum eigenvalue of this matrix has to be null. So our modus operandi will be to consider symmetrical designs. After that, we will compute the optimal symmetrical design, and after that, we will check this condition to guarantee to have obtained the optimum. Well, let us define mu j and kappa j as the jth first and second order moments, respectively. And from that, we are able to compute the matrices in the D loss. Note that they have a high number of null elements as consequence of the affine transformation and of considering symmetrical designs. And thanks to that, we can obtain the formula for the D loss, an algebraic expression for the candidate's eigenvalues. Well, let L1 and L2, the loss function, evaluated over rho 1 and rho 2 respectively. And in order to compute the minimal density, we are going to use the following general construction strategy given by Daimi and Beams. It consists on partitioning in a subset where each of eigenvalues is a maximum, and over each partition we are going to compute the minimizer density, and then the minimizer will be evaluated over the loss for the corresponding eigenvalue. And the design giving the minimum value will be the global minimizer. So we have to solve several minimization problems, one for each candidate eigenvalue. And the first one will be the problem to seek the functional M, minimizing this expression, subject to that the M function has to be a probability measure, obviously, and the first order moment are included into the problem as a boundary conditions. And the fact of being in the first part of the partition of the design implies that the first eigenvalue is higher than the second one, and this inequality can be transformed into an equality adding this slack variable and add it to the problem as another boundary condition. Well, at this point, using the theory of Lagrange multipliers and some variational methods, we obtain the following expression for the optimal density. The sign plus is referred to the positive part of this function. So the next step will be to determine the values of these coefficients using a minimization routine in MATLAB and verifying the boundary conditions. Well, now I'm going to show a movie which contains the evolution of the optimal rows design as nodes varies from 0, variance is only considered, to 1, bias is only considered, and variance is completely ignored. As we can see, in the case of classical or quasi-classical the optimal rows density, we have that there are more design points in the extremes and in the middle of the design region, and then the more importance is given to the bias, the more uniform is the distribution of the point allocation throughout the design region. On the other hand, we want to provide an exact design to the experimenters, and in that case we have choose the deciles for being converging weakly to the optimal design and for being the closest to the 10-point exact design in the sense of homologous distance. Well, now we want to extend this theory in the case of ternary blends. When following the same reasoning, we have that we face another problem, and it is that the matrices necessary to compute the D and I loss are these order matrices, and although simplification were tried, we couldn't obtain an analytical expression in this case for the eigenvalues. So our solution was to discretize the problem and to compute numerically the eigenvalues and provide a new methodology for the loss minimization. So we provide heuristic algorithm based on genetic algorithm because of they are very fast and computationally powerful. We have developed a genetic algorithm with a specialized operator in order to deal with the special nature of mixture experiments. Well, this is the guideline of the genetic algorithm. We start with initial population of m nth point exact designs, then a probability measure is assigned for each design regarding their goodness respect to the populations 1. Then the best design of the current population are remain unchanged for the next generation of new designs. And then two parent design must be selected randomly but proportionally to their fitness value. Then, under certain crossover probability, the two parent design, and crossover operator we call to act. Otherwise, the new child design will be the best parent. Well, I think that the key point of in genetic algorithm is precisely the crossover operator. We have defined a new operator named unitary crossover, which consists of keeping the maximum number of observations of both parents for each design point in the discretized region. And then this fact generates an excess of probability which is progressively deleted by a randomization process. Well, other key point in a genetic algorithm is to keep the biodiversity in the solutions in order to avoid to get trapped into local maximum. So in this sense, the algorithm has to provide more opportunity for new solution when it is far from the optimum and to reduce the biodiversity otherwise. So we have to establish a mutation probability which will be updated regarding the stage of the algorithm. Under certain mutation probability, the mutation operator we call to act. Otherwise, the new child design will remain unchanged. And this mutation operator consists on replacing the current child by a random permutation of the coordinates of the previous child. Well, the process is from probabilistic selection to mutation, having to be recursively repeated until having completed a new generation of M designs. After that, if the best of design of the current population has remained unchanged during a sufficiently high number of consecutive iterations, it is the optimum, and otherwise we have to update the initial population and repeat these processes until verifying the stopping rule. And now there are some examples of D and I optimal robust exact design obtained with this genetic algorithm. They are 24-point exact design. As we can observe, in the quasi-classical cases, the design points are around 3 to simplest lattice, a kind of standard design. And when nu is equal to 0.1, we deduce likely a 3-3 simplex centroid. However, in the case of the variance is almost ignored, we have that the point allocation is freely distributed along over the simplex. However, we find that for I-optimal robust design that the 3-3 simplex centroid is invariant as nu varies, and we think that it is a very important design feature for practitioners, because they have to choose always this design regardless their knowledge about model adequacy. Well, following the idea to get an analytical result for ternary blend, we want to consider a restricted class of design, and motivated by the idea of the following idea. It is that the most of the obtained design verify the property of symmetry throughout the three medians of the simplex. At this point, we have not achieved an analytical result, but we have some numerical result in this sense. The property of symmetry throughout the medians of the simplex is algebraically translated as the invariance by any permutation of the coordinates of the design points in the design. And this property has been named as exchangeability, exchangeable designs. So we find, considering this kind of restricted design, two advantages. The first one is that they are more accurate in the point allocation around the standard design, and on the other hand, the computational cost is lower than in the general case. However, in the case of more freedom is needed for the general design, in this case, exchangeability can be a very stringent property. So we have suggested another class of more flexible restricted design named partially exchangeable design. And here there are some examples in which the design point only verify the symmetry throughout one of the medians of the simplex. And we have the same advantages than in the previous case, and in this case the problem has been solved. Again, following the idea of achieving a theoretical result for ternary blend, we have considered another more restricted class of design named symmetric partially exchangeable design, which are formed by subset of points of this form, and this kind of designs only take sense over a subregion of the simplex. So only taking into account all these assumptions, we are able to extend the methodology for binary blends to the two-dimensional continuous problem. And in this case, we obtain the analytical expression for the optimal D and I robot design density. And now we are going to show the evolution of the symmetric partially exchangeable D optimal and I optimal robot design over the subregion of the simplex. We found the same behavior as in a binary case. In the case of quasi-classical, the design points are allocated in the extremes and of the design region, in the center of the design region, and in the midpoint of edges. And then, when bias is more emphasized, the density is almost uniform. And then another goal is to provide an exact design for practitioners. So in this case, we have used the following scheme of implementation. We have found the exact design minimizing the differences between the empirical moments and theoretical moments given by the analytical density previously computed by the previous procedure. They are the D and I optimal discrete design over the subregion in which this class of restricted designs makes sense. Well, and finally, we have applied this methodology in order to solve the real problem laid out by the machines and motor area from the University of Castilla-La Mancha. Well, the commercial fuels are formed by hundreds of hydrocarbons, and it's not possible to reproduce the oxidation chemistry for all of these. So the kinetic studies only consider a small number of the most important families of hydrocarbons. They are paraffins, aromatics, and naphthenes. Well, the phenomenon which has been explained throughout the second order Shefe canonical polynomial is the differences between the ignition delay angles obtained with the surrogate and original diesel fuel. Well, we provide to the practitioner different the optimal 12-point exact design computed by our genetic algorithm for several new values. We also provide the laws obtaining with each design. We also provide some efficiency since the standard designs have been the most widely used by experimenters. We want to consider this class of standard designs when bias occur. And in that cases, the efficiency of this standard design are very low in comparison with the designs obtained with our genetic algorithm. Well, now we fit the response throughout a traditional method. Remains that the response measures the differences between the delay angles between surrogate and original diesel fuel. So the optimal composition is one minimizing this response surface. So using a minimization routine, we obtained the following optimal surrogate composition, which is very close to the original diesel from data from the literature. Well, to sum up, the concluding remarks are the problem of designing when there is a lack of model of knowledge about model adequacy is investigated. We have provided some theoretical resource in order to obtain optimality condition for the symmetrical D-optimal continuous design for binary blends. Thanks to this fact, we are able to obtain the optimal analytical density for this case. And on the other hand, we have provided a new algorithm with an operator specialized in mixture settings, which is general. It can be applied regardless the number of ingredients in the mixture or the considered model. We also provide a class of resistive design which reduce the computational cost, and they are more accurate in the point allocation. We also provide an approach of the continuous problem for ternary blend, but the obtained designs are not as informative as in the general study case. So, and the previous methodology has been used for solving a real problem related to the automobilistic industry. Regarding open lines of research, we want to prove theoretically why it happens that the three simplest centroids is invariant as nus varies, and in this sense we have proved this relationship between the two matrices addend in the ILOS, but we are exploring new possibilities in this vein. And on the other hand, we want to split the simplest up symmetrical exchangeable subregion to handle the continuous problem with more than 2 ingredients. And on the other hand, we think that the exchangeability property must have good properties considering another class of model, Kronecker polynomials models. We want to extend this theory for the case of mixture nonlinear models, since they are the most widely found in real applications. There are some references, the most important references used in this work. I would like to thank to the Professor Douglas Gins, because much of this work was done during one research stay that I was doing in the University of Alberta in Canada. And thank you for your attention. And that's all. So, any questions?
Okay, questions, Irene?
I've got one. So, you've basically got two approaches, right? One is to find an optimal density, and then choose some discrete points by some summary of that density, maybe quantiles or by comparing moments. And you've also got a second approach, maybe you did this first, but it's a different approach, where you just discretize the whole problem, discretize the design space and find an optimal set of finite points back. I was just wondering which approach should I use? What is the effect of using one or the other? Which is better?
We think our goal was mainly to achieve a theoretical result, and in that sense we prefer the continuous problem. But when it's not possible, we have to discretize the problem compulsory. So the thing is that although continuous designs are considered, we have to provide a discrete design to the experimenters, and we find that in the case of ternary blends, numerical or designs compute by numerical techniques are better than continuous design. So we have, on the other hand, one advantages, and on the other hand, disadvantages. So there is no a winner design, continuous or discrete, in that sense.
Any questions? So I have a question. So when you're finding a design, you're worrying about this potential when you do your reward fitting and your optimization, you just base it off the assumed model. Could the contamination turn affect the optimization problem once you've got the data?
Yeah. The problem of the maximization over the Haber class of functions, in which the contamination function belongs to, is taking into account seeking the maximum eigenvalue of these matrices. It is equivalent. There is an equivalent problem thanks to a result given by bins. So we have we take into account the contamination function in that sense, computing the maximum eigenvalue of this matrix. I'm checking the result. No, it is here. No, in the following one. That's one. To do the maximization over the contamination functions is the same that to do a maximization over the real line thanks to this result. Mm-hmm.
If you could go like 3 slides earlier, please.
Earlier?
Like slide there. A little bit after that. Go ahead, please.
Okay.
Earlier, there is like 10. I think it's
10?
10. 10. Yeah.
It is.
So, it of course is different, but it looks almost, you just look with a half of open up, like creating, doesn't it? That psi of x is, you will be using like, it will be the correction bias term, could be. And then the question is, of course this is different, but have you thought of comparing the results of the methods you have done with something that you would obtain with something like creating, like a stochastic process? Because your psi functions, of course they are not random, they are other things, but they have like a zero expectation and some bounded variance. They are not random variables per se, so I'm only pointing at the right direction. So have you thought of comparing what you have done with creating, picking the trend that you know, and then some stochastic process on top, compare what happens?
We have no. We haven't investigated this point, but maybe in the future. Thank you.